If you have an opinion that calculus is hard and impossible to understand, you are at the right place, because I will give my best to show you that anyone can learn basics of it successfully, just in the length of this video. Before we dive into calculus, I must say that I have noticed that many of you guys who are regular viewers of the channel have not subscribed. So please subscribe, as that support helps me a lot in my efforts on the channel. Now, to return to the topic, this video about integration and derivation is going to be done in the way that does not require any knowledge of algebra or trigonometry. The idea is that only with knowledge of basic mathematics you can understand the topic presented here. Let's start with calculus. As you can see here, I have a couple of shapes. I have a circle, a rectangle, and a triangle. Our job is to find the area of each of these. Area of circle can be found by using the formula that area is equal to r squared multiplied by a constant pi. R is the radius of the circle, the distance from the center of that circle to its edge. As you can see, if I know what r is, I can plug that information in the formula and then calculate the answer. On the second picture, I have a rectangle. Let's say that L is the length of its side and that W is its width. The area of this rectangle can then be found by using the formula that A as area is equal to length multiplied by the width of this rectangle. Finally, on the third picture, I have a triangle. As you know, the area of a triangle is 1/2 multiplied by b multiplied by h. This b represents the length of the base of a triangle here, and h is the height of the triangle corresponding to that base b. As you know, this angle right here is a 90-degree angle. It is a right angle. By using these formulas, I can without any problems calculate the area of any one of these shapes: a circle, a rectangle, or a triangle. The catch, of course, is that I have to know the formula of an area for each of the given shapes. Naturally, a question appears: what should I do when I encounter a problem like this one? And here we have to find an area of this shape under the function. So as you can see, this shape has a boundary made of this curve here. Its other boundary is the x-axis, and it has a boundary y-axis. Its other boundary is the line x is equal to 10. At this point, we don't know how to find an area below this line. Let's call this a function f, this shape of a curve right here. We only know how to find an area of a circle, rectangle, and a triangle. What is the area below this function f? In this problem, there is no formula that will give us an area of this shape. We were able to use those nice formulas to calculate areas of a circle, a rectangle, and a triangle. But for this shape, such a formula simply does not exist. To find this area, we have to change our approach to this problem. Integration is so important because it's a tool that can calculate the area of any shape that you can want. The power of integration does not stop there, as the same applies for the volume. So how does integration work? Let's focus on what we know how to do. We know how to find an area of a rectangle. Then the idea is to find a good enough approximation of this shape below the function. So let's take in some rectangles. We are going to take this rectangle to be our first rectangle below the function f. Then we are going to use, let's say, this rectangle right here. And then we can use this rectangle to approximate the shape even better. So this one right here. Then we can take this rectangle and so on. We are going to cover with rectangles everything that is under the function f. We are then going to calculate the area of this shape under the function f by calculating the area of each of these rectangles and then adding them all up together. And by doing that, I would get an approximation for the area under the function f. So integration is conceptually going to use the area of a rectangle to give us an approximation of an area under the function f. The power of integration is that it can be used to calculate an area of any surface, not just this one. So we can use integration to approximate something that we don't know by using something that we know. Now in this picture I have taken some arbitrary rectangles to give you a feel of the concept. Now we are not going to do that by using any rectangles. We want more control of the process. So we are going to gain that control by using the rectangles like this. So we are going to be using only these vertical rectangles for the purpose of gaining that full control of the process we are trying to make here, the integration process. As you can see, for each of these rectangles, I can read their dimensions from the Descartes coordinate system. From the x-axis, I can get the information of the length of the base of a rectangle. So this will be the information of the base for this rectangle. From the y-axis, I can get the information of the height of that specific rectangle. And I can repeat that process for all the rectangles that I have. In order to get the area of this shape, I just have to add up the areas of all of these rectangles. And this is exactly how concept of integration got invented. So the problem that we are hitting now is the precision. Using all of these rectangles, we have approximated to a certain degree the area of our shape. But we don't know the exact area. We just have a number which is near to the real thing to some level of precision. What happens if we need an answer to be more precise than what we have currently? The only way to get a more precise approximation of area of this shape is to use more rectangles. Now to get more rectangles, I am just going to divide the existing ones. So observe this rectangle here. We got this area as approximation for the area of this part of the function. Now, if we divide that rectangle into two rectangles, we are going to get a better approximation. We have this rectangle here, and as you can see, by adding this part over here, we are going to get that better approximation. We are going to do that with all the rectangles. So the only way to get a more precise approximation of area of this shape is to use more rectangles. So we are using more rectangles of the even smaller base than the ones we used previously. I'm not going to cover an entire shape with these rectangles, but you can understand what I am doing. So we are using the skinny rectangles, and if we need even more precision, then we are going to use even skinnier rectangles. As you can see, I am still working with rectangles, nothing has changed. There is just more of them, and that is making my approximation better. The idea here is that if you want to get better approximation for an area of a shape, you have to use finer rectangles. The finest rectangle that you can make is the one with an infinitely small base. And this is the main concept of integration. The finest rectangle that you can make is the one with the infinitely small base. Just remember, this here is the base of this rectangle. And this is the main concept of integration. We are going to add up all of these rectangles of an infinitely small bases together, and that sum is going to give us a precise area of a shape below the function f. The notation of an integral in our case is a sine of integral. Integral goes from 0 to 10 f of x dx. This notation means that we are taking our function f, this function right here, and that on the x-axis we are starting from number 0. 0 is the lower border of our integral. And we are going all the way up to 10. As you can see, number 10 is the upper border of our integral. And we are adding together the areas of all the rectangles underneath this function f. The rectangles, remember, that have a base of infinitely smaller length. This elongated s here that we use as a symbol of integrals originates from the word sum. So we are taking the sums of all these rectangles underneath the function f. And as I have said, these numbers 0 and 10 are borders of our integral. And they mean start at 0 and go all the way up to 10 and add up the areas of these infinitely tiny rectangles under the function f. So the integral is what we are using to find an area of any shape. In order to use an integral, we have to know the function f. We have to know the boundaries of our integral, the point at which we are starting the integration and the point where we are ending it. For example, let's find the area from 5 to 10. This is that area right here. Our integral has different borders. It will be an integral where we start integration at number 5 and we are going to integrate all the way up to 10. And the function, as you can see, is unchanged. So we have f of x dx here. Remember that this function f, which we are using in our example, is not the only function that this method works on. So we can have something like this. We have a Descartes coordinate system, x and y axis and origin here. The function can be integrated at any interval from a to b, and that function can have any shape. It can look like this or it can look like this. It doesn't really matter for integration. Or I can have any other function that you can imagine. And for borders, as you can see, I can go from any number a that I can imagine to any number b that I can imagine. Integral allows us to calculate an area of a certain shape, but remember that we can also use it to calculate a volume. And as you can see, we don't have here any exact formulas for an area or for a volume. Integration is a method and there is its power. You don't have to remember any formulas. Just learn the method and apply it. In order to fully explain the concept of integration, I have to also explain what this dx here means. Dx is a derivative with respect to variable x. And let's explain what dx is with the help of another example. Let's say that I have a road here and at this position I have a car. So let's observe this car, which is going to accelerate in this direction in the straight line. The car starts with 0 kilometers per hour. That is its speed. Or you can take 0 miles per hour for my non-metric audience. I know that there are some of you guys who don't use metric system. It's probably too communist for you. And this car is going to increase its speed all the way to 80 kilometers per hour. Now, a little calculation here is required for you non-metric users. So this is 49.6 miles per hour. It's not exact, it is an approximate value. So the car is going to increase its speed all the way to 80 kilometers per hour, and let's say that it does this in 10 seconds time. Conversion for kilometers per hour to miles per hour is that 1 kilometer per hour is approximately 0.62 miles per hour. The question is, if the car goes from 0 to 80 kilometers per hour in 10 seconds, how fast is this car going in the 3 seconds? So at this position here, which is 3 seconds. We need to precisely calculate the speed of the car at a 3-second timestamp. The car is going to continuously increase its speed for these 10 seconds. If you think of the formula R multiplied by T is equal to D, so rate multiplied by time is equal to distance, you are not going to be able to use this formula in this case. This rate in the formula is fixed through entire time of the experiment, and here we have that the car is continuously increasing its speed. So in each dot of this distance, the car is going to have a different speed. So this formula RT is equal to D can be used in the case that this car is going down the highway and then that it is going all the way with constant speed of 80 kilometers per hour. We don't have that here in our example. In this RT is equal to D, it's easy to calculate rate and distance because the velocity is the same. However, when we are accelerating how fast the car is going at this particular moment in time, that problem is completely different. We need to use the mathematical tools provided in calculus to give an answer to that question. Specifically, we need to use the tool called the derivative. So the derivative solves the two problems that we have. One is instantaneous velocity question like this example with an accelerating car. The second thing that it solves is the area problem which we were dealing with previously. Of course, these two problems are not the only ones that the concept of the derivative can be applied on. That concept of the derivative is much more versatile. And then there is a concept of integration. So we can find these areas not only of simple problems like area of a triangle, a rectangle, or a circle, but we can find an area of an arbitrary shape below some function, or we can use it to find a volume in a higher dimensional case. Now, both of these concepts are a part of calculus, which is one extremely useful area of mathematics. I am going to make an entire series of lectures about calculus, and in this video I have showed you a bunch of those problems which are going to be solved in calculus on a regular basis. So you can now see for yourself, understand that extreme importance that calculus has obtained by the value of problems that it can solve. I want to encourage everyone to explore calculus. I know that people are mostly trying to avoid it as much as possible. Yes, there are a lot of challenging things, a lot of rules. I am not trying to give an impression that it's not a challenging part of mathematics. But the beauty of it is that it can solve a lot of the real-world problems. So thank you for watching. Please subscribe to the channel, and if you want to learn more about calculus, please follow the links in the description.